So the main approach that we have for solving it, which we talked about a bunch of times already now, is that we're doing gradient updating, right? And so now we've got this big function with all these weights, right? A large number of weights here for every hidden layer. And if we have multiple hidden layers, then this part's going to be duplicated many times, right? So you just would have more elements in your function here. Every one of those weights, you could compute the gradient, basically relevant of the change in that output function of the entire network with respect to that weight, right? So if we move that weight up or down a little bit, how would it affect the output, right? That's all our gradient really means. And since everything's linear and every function in it has a gradient, we can always break this down into partial derivatives for every weight individually. Of course, it's a very complex function, right? It's not going to be convex unless you have kind of some very strong assumptions on it. And if you just have a simple, I guess in linear regression, it's convex, but it's a very simple function, right? We have many combined functions here, so we don't know the shape of this thing, so we have to solve it iteratively, right? I've got incremental gradient descent. Right, okay. So, I mean, we talked about this with logistic regression, and with my functions, what are we saying? Oh, sorry. That's what happens if I use the mouse. Right, okay. So here we've got, for every one of these functions, we have our output label, which are going to be our y's, and the output, these O variables are going to be outputs of any particular layer. And we're just going to be computing the difference of those to get our error, like how well are we doing on matching the labels versus what the output of the last layer is. So the general idea, right, is that we're going to be computing the gradients on all those weights and then updating them as a scaled version of the error or the loss, as someone was saying, and using that to change them in a way so that we want to basically move them towards values that make more accurate predictions, right? So if a weight was contributing to high error, and if we had high error on a prediction and that weight's gradient is strong, that means it was a large contributing factor to the output. We want to reduce its value, right? That's the main kind of idea. But then as an algorithm, we have to kind of do this iteratively across the whole network, right? So this is just what I was saying before, kind of derived out in more detail for the whole network, I think. Yeah, but our last when we have that derivative for the different layers combined together, the idea is that we're going to be computing that on each of these units in the network. So what I had before was, right, this is the output of the network. These are the labels that we're trying to adjust to. And then we've got the deltas, the changes we're going to have on every one of the layers. So for the last layer of our network, right, it's our hidden, it's our output, it's our input. We're going to have our delta K on kind of the changes from this layer. And then after we compute the changes from the next layer in, we're going to use the ones from that, and we just chain them along, right? So the gradients from one layer contribute down to the ones for the next layer. And every weight along the way is going to get updated. So for every weight in the network, then we're going to have this function that tells us going forward from that weight, to the end of the network, everything that it kind of influences, combining together all of the weights and the gradients that we observed using that kind of error, and then make this small change, right? And so backpropagation is kind of implemented and used in all these networks broadly, and that was the original method. Even in the 80s, it's quite an old algorithm. So fundamentally, it hasn't changed because that's what you have to do, right? There's tricks of optimizing things and what these functions should be, but in the base function, the base idea of this backpropagation, there haven't been huge structural changes. And some of the people who invented it actually complain about that. They say, why don't you guys innovate more? Like, come up with a new way to update everything. But it seems like quite a powerful thing. But it really is just the idea that you're chaining the gradients. The error for every output node, computing its gradient, using those weights to go backwards, and then collecting them in an organized way so that you update the entire network. So that's one pass from backpropagation, right? You get some output, and you push them back, and you do an update. You still hear me? Hopefully.
Yes, we can still hear you.
Yeah, okay, great. So that's people ask me we're rushing. We don't have to rush. We can go back. We can go into it deeper. I'm just giving the main idea of that. Because it's a gradient method, right? We're not optimizing, so it's important to remember that, right? We're not finding some optimal solution here to the best possible weights for the network. It's really always just an incremental update based on those outputs. Oh, that's an error. That you've seen from the evidence you've seen, right? So that error that is being computed is really from the training data you have, and you can only make local updates on it based on that, right? So we don't have any guarantee that we're getting to something perfect. But are there any questions about what the parts are and how they work?
Yeah, I guess could you go over the notation on backpropagation? I kind of missed what those deltas are and what the primes mean.
Sure. Let me see if I have this. I have my own version of the note. I should just show that one to you guys. How do I switch? Can you see that one? Yeah. So you have a bit more notation on this one. Right, so we've got I had a diagram before. I guess it's in the other deck. I reconfigured some of these slides. One of them in a different slide deck. So the O here is for the output value for the whole. Well, the output value for each layer, right? So if we've got K, oh, I had the network up there before. For any individual layer, K, you've got some output values, and everything's prime in this value. Oh, it's not prime; it's L, right? In the derivation we have here, we're summing over the nodes of the inputs. So L, yeah, I shouldn't use L then. I should update this. It does look like a prime. It's just over the nodes. So K is the index of the layer, and the thing
I
looks
actually
like
think
a prime.
the L. I actually think the L is the layer number, right? Not K. Because here you're summing the negative sum over L, so you're taking the output of the the Y output for layer L minus the O output of layer L, right? So this is the true answer versus the predicted answer over each layer, I think, right? That's why they use L, right, for layer. So.
It sounds right, yeah. Sorry, I haven't looked at this notation in that detail in a while. Just go, it works. The I's individual weights. Sorry about that. But then the K, I guess the K could have been the node index for that one, because they have I and J, which makes more sense with the notation thing. So I just got to swap around in my head then. So yeah, the lower case, thank you. The lowercase subscript would be the index of the node itself, like the weight for weight I. And on this next slide, right, we've got the output for node K in layer L, but then they're all L. I mean, in this one, it's definitely all consistent because it's from.
I think so. The two, I think, if you go back to the previous one that you had.
This one.
Yeah, so you have the two subscripts I and J because they're going from weight I in one layer to the next weight J in the next layer, because it is a transfer weight between two layers. You have to say
for every pair.
In one layer, you're going from weight I to the next layer weight J. So those are the two connections in, and then for some layer L, right? But it's going to be indexed so that you're kind of.
Yeah, I might have just dropped
zero
the whole
to n-1 layers, right? So, but yeah.
I might have just dropped the layer thing that was iterating over the layers when I was updating this slide last year, probably, and then no one caught it. Yeah, so maybe I should update my slides on this so I have something more consistent, because it probably is a more updated way of doing it. But yeah, so I'm not completely sure if that one's all perfect. So this one is older, but it should be all self-consistent. So in terms of here, if we're going through every layer, then you're always computing it locally for that layer, right? What's the gradient? Because in net, the way we had it before, net is kind of the the output signal of that first layer, right? So that's why L, I'm still not sure. And so you're talking about what's the change of the activation function sigma with respect to the outputs from the net layer, and chaining that. But I should find a more complete and updated notation for it right now, and point you guys to it, because there's lots of more recent descriptions out there about how all this works. So. But do anybody have questions about the high level?
Yeah, no, I think that the high level makes sense. It's just
Yeah.
like the mathematics for the partial derivatives as we chain backwards can get a little bit convoluted.
It does, yeah. And like I said, I mean, you don't usually look at that very much once you've set it up, because now it's about the structure and like the choices of the functions and the architecture. Most people spend time thinking about different architectures and the effect of that, and take a lot of this for granted. But it's good to know it. So I'll find you guys a better resource that's more up to date. I've been wanting to update this anyways. I just always leave it behind in focus in favor of kind of newer things. So, but it's fair. You guys engineers, you should be able to build it from the bottom up as well. So I'll get back to you guys with some stuff on that. So I guess the final slide on this topic anyways was about that idea that essentially the default approach for updating is just this simple kind of gradient descent. And there's been, like I said, the essential idea that you're updating gradients and moving backwards hasn't changed, but the kind of approach for how to combine those together, there are other methods. And so the atom is kind of the default one you'll often have in a lot of libraries now. And it still uses gradients and updates individual weights that way. We have, but it adds additional ideas into the formulation, like momentum. And so rather than just updating a weight directly, you add a bit of resistance to it changing its value. So it's kind of almost a thresholding, but on the gradient updating step. So you have to have enough of a difference for it to make a change, and then you actually can update the weight. And where we had the error, where we were using, the difference between the label and the output squared, right? They'll combine in other things and use the variance as well. So you're trying to reduce the error, but also trying to reduce the variance, right? So you don't want the outputs to actually, you want to become more sure of its own things rather than just maximizing the accuracy of the output. And that's going to make you more robust to different data sets and things. And there's even ways to do, LFS BFGS is another gradient approach, but it tries to take more, do more efficiencies by using it, treating them all as a matrix formulation of the gradient and doing it all kind of in parallel and more quickly. But it's another thing that's becoming popular. But this one was another one of the big, the change to using ReLU as the activation functions and switching to kind of this improved gradient updating, like Atom, were kind of a couple of the big changes that led to deep learning kind of becoming more successful than the original neural networks had, or more than SVMs. Because like I said, back in the 90s, early 2000s, like support vector machines with basis functions and all these things were working really well. So you had to beat that. So a couple of these things started happening to help them beat that. But the other part that happened was adding more hidden layers, which is where the deep comes from. And we'll talk about that tomorrow. We're going to more like other ways to train this, because once you start adding, everything we're talking about here is just for, works just as well for just one hidden layer. But if you're adding more hidden layers, then you get into other problems that can arise. And so you have to kind of fix those first before it can work. So effective deep learning is the next slide deck, which we'll go through tomorrow. And like I said, I'll try to get you a better, more concrete description of the backprop formulation, because I've been meaning to update that anyways. Okay, so there's some comments. So I'll end there, and I'll just look through the comments, see if there's any. There's a bunch of discussion. There's people talking about unsupervised learning and anomaly detection. So yeah, I mean, I agree with what people are saying. Right? Supervised learning is makes the most sense with this, because full function, we're taking that output signal and updating all the weights in the entire thing. But there are ways to do things that are unsupervised and kind of self-supervising on their own data, and we will talk about that a bit too. But supervised is the simplest way that makes sense, and it gives you the most powerful models. Obviously, it requires you to know the main answer. So it's not impossible. It's just if you're going to do unsupervised, and what are you training on? You need some signals. So if we're talking about updating this, right, you need a way to say, what's your, well, that's just the gradient, right? You need a way to say, what's your loss going to be? What's your error, right? So if you don't know what the right answer is, how can you compute this error, right? So you can compute errors like we saw in clustering and anomaly detection. You could say, well, there's some property of the data. I want it to tell me that similar points are near each other, or different points are far apart, given something I know about points, or something that you can do, which is kind of self-supervised learning, which we're going to talk about in autoencoders, where you basically say, can you train a model to regenerate the data you gave it? And that's a very strong signal. And you say, well, if you can basically recreate the data that was the input, then you have what's called an autoencoder. And that's not supervised in a sense, because there's no new label being predicted, but you can basically repredict yourself. And that sounds like it might be a silly idea, but it's actually very powerful, because in order to recreate your original data, you have to have the hidden layers encode everything about how the data is related, how all the different kind of aspects of it. So all of the deep fake stuff you guys see, or those things where you can like turn your photograph from your phone into like a Van Gogh painting or something, those use that kind of idea that you kind of trained it on a model on itself, and then created a generative model to create new things. So there's lots of ways to do it, but the supervised learning is kind of the core way of understanding neural networks. Everything else is extensions of that, or playing with how you do it, right? And good question about anomaly detection for unsupervised learning. I'll think about that, and we can talk about that in a later time. Once we're doing some unsupervised neural networks, we can come back to that. Because there are ways to do it. It's kind of more recent methods for anomaly detection that use neural networks, and I'm not as familiar with them. But the talk actually recently, no, that wasn't about that. There are a lot of methods now that are using that, where you basically train a neural network unsupervised or self-supervised data somehow, and then build anomaly detectors from that. So there's a lot happening. It's just a bit more challenging because they are set up essentially for supervised learning. Okay, so I'm going to end there for today. Thanks, everybody. And I'll see you tomorrow.